So far we have discussed the Baskin equation, which seems to work actually quite well for high cycle with fatigue. It's a stress-based approach. We take the stress as an input and predict the corresponding fatigue life, or vice versa. Given the life, we can predict the fatigue strength. But there were 4 major shortcomings, and we want to now address them one by one in order to widen the applicability of the Baskin equation. And the first thing we're going to look at, the first among those 4 items, was the effect of mean stress. And so what we're going to do is we're going to draw first stress life curves. And so here the horizontal axis, as usual, it's life, and again that's almost always the log scale, and the other axis is the alternating stress or the stress amplitude. That's a linear scale. And we have our usual stress life curve that looks like this, may or may not go to an endurance limit. So if we concentrate at a given life, so a given number of cycles to failure, then the corresponding fatigue strength is delivered by that point. Now, the curves that we discussed so far and the curve that is also described by the Baskin equation assumes that the mean stress is equal to 0. Now, I'm going to ask you a question, and I'd like to think about the answer to that question for a few seconds before you move on in the video. Now, if mean stress is 0, for a given fatigue life, this is the alternating stress that I can apply. If I want to achieve the same life, but the mean stress becomes positive, can I keep the same alternating stress, you think? If not, shall I decrease it to achieve the same life, or shall I increase it? Alternatively, if the value of sigma m becomes negative, becomes compressive, in order to achieve the same life, can I now apply perhaps higher stress amplitudes, or should I apply lower stress amplitudes? So think about that question for a few seconds. Now, if you've done so by pausing the video, recall that we have in fact discussed a similar case in the case of crack growth. So, and our discussion concluded from the case of crack growth, it also applies here, concluded the following. Now, if the mean stress increases, what's going to happen is the cracks or the fatiguing structure is going to spend more time under essentially higher positive tensile stresses for a given stress amplitude. Okay? And therefore, if you keep the stress amplitude the same, if sigma m increases towards positive values, what's going to happen is the situation is going to become more critical, and therefore the fatigue life will decrease. If you want to keep the fatigue life constant, therefore, you better decrease the corresponding value of the alternating stress. Now, alternatively, if you, for a given stress amplitude, if you make the mean stress negative, then now the structure, the fatiguing points in the structure spend more time under less positive stresses because sigma mean is negative, and the situation becomes less critical. In other words, for the same stress amplitude, you can achieve higher lives. Or if you want to achieve the same life, you can actually apply higher stress amplitudes. So if you apply negative mean stresses, the curve shifts up, right? So for the same stress amplitude, you can achieve higher lives. Or if it's positive, the mean stress, then the curve shifts down. Or in other words, for the same given stress amplitude, you will achieve less life. Okay, so no matter how you look at it, essentially the information we're providing through this discussion is that as you move in that direction, the mean stress is becoming more and more positive. It's increasing in value, and in fact, if it becomes even more positive, then this curve will shift even further down. Okay, so now what we would like to do is we would like to represent this picture by drawing the green line on a new plot. Now, what's changing on the green line is the combination of alternating and mean stress values, they change, but we always have the same life to failure. Okay, so for instance, now if I make this vertical axis against sigma A and this one sigma m, both of them linear normal scale, so if sigma m is equal to 0, I'm at a certain point where it's completely reversed and therefore I have a certain number of cycles to failure. Now if I want to achieve the same number of cycles to failure with a negative mean stress, so I'm going to plot a point over there, then I can apply now a higher alternating stress. So let's say that stress is going to be over there. And if I want to achieve the same life with a positive mean stress, then I better apply a smaller alternating stress. Okay, so this one is completely reversed, negative mean stress, positive mean stress. And now I can pick many such combinations, values of mean and alternating stress, which lead to the same life, and combine those points on a line. It turns out that that line looks something like this. So because all combinations of sigma A and sigma m which lie on this line, because they lead to the same number of cycles to failure, this is called a constant life curve. Okay? And notice that this is not, in general, a straight line. Now, what we can do is we can pick different green lines, points that are to the right and points that are to the left. Okay, so then I will get different lines here. So if the line shifts up, the number of cycles to failure decreases, because here, for instance, is completely reversed, and I know that if the stress amplitude increases, number of cycles to failure decreases. But again, by changing the mean stress, I can generate different curves. Those curves can look like this. Okay, so when I move in this direction, the number of cycles to failure is increasing. Okay. All right, so now when I look at this picture, what I am seeing is that there's a general trend in which, of course, if we apply higher mean stresses, right, and if I want to achieve the same life, the alternating stress has to decrease. And in fact, if the mean stress is very high, the alternating stress I can apply is almost 0, which is what I see from these curves. They seem to go towards an intercept which sort of agrees for all of them. So they may not intersect at a perfect point, but essentially there is a region here, okay, somewhere here, where the mean stress is so high that we are able to attain very small number of cycles. Okay, and this is where we are approaching failure despite the fact that the alternating stress is almost 0. Okay, so we're going to approach failure despite the fact that the mean stress is so high, the alternating stress is going to 0, but still we get failure. In general, that's going to occur with a very small number of cycles. Now, remember an earlier picture. Earlier, we said that when we were discussing the value of sigma f prime that appears in the Baskin equation, we said that we can look at a scenario, a completely reverse cyclic loading that was the case in earlier discussions. In that case, we said failure occurs at first peak if sigma a is sufficiently large. In other words, if sigma a is approximately equal to sigma f prime, which we then associated with something that has to do with failure in a uniaxial tension test. An experiment indicates that sigma f prime correlates very well with the true fracture strength of the material. Now, in the present case, it's not sigma m going to 0, but rather a different scenario where sigma a is actually going to 0, and sigma m is becoming large enough to cause fatigue failure, or in fact failure with a very, very small number of cycles. Okay, so now we're talking about failure again. Well, when we say failure, well, we have several quantities that we've associated with failure earlier. So we've looked at, for instance, the yield strength. We've looked at the ultimate strength. Well, we can also look at the fracture strength. Now, what type of fracture strength? The true one, or the engineering one, or perhaps something that is yet again meaningful in the context of fatigue, sigma f prime, which is very close to actually the true fracture strength. So in general, however, it doesn't matter conceptually which one we pick. We are going to pick a critical value. And for these critical values, I will be eventually assessing whether, or using this critical value, I'll be assessing the influence of the mean stress. As the mean stress approaches this critical value, the amount of alternating stress I can apply to reach the same fatigue life. As the mean stress increases, the alternating stress keeps decreasing. Okay, so that's the observation. How far can I go in that discussion by increasing the mean stress? Well, until the mean stress reaches a critical value. That's where the alternating stress should take zero, essentially, value, because even a tiny alternating stress will cause fatigue failure. All right, so now, therefore, if we combine these discussions, what we're really going for is a situation of the following type. Now, first of all, what we're saying is we have the Basquian equation. The Basquian equation, in fact, let me write this in red. The Basquian equation is, and I'm doing that to emphasize the nature, it's for completely reverse loading. So the alternating stress with a zero mean stress. So sigma m is equal to 0. So in that case, the Basquian equation tells us a relation, gives us a relation between the stress amplitude completely reversed and the number of cycles to failure. So that's what we have. All right, good. Well, on the other hand, we have all of this discussion which tells us, well, suppose somebody tells us what the number of cycles to failure is, and what we are now deducing is that if the mean stress is greater than 0, I cannot apply this alternating stress, which was for completely reverse. The actual one I can apply is actually less than that. Okay? And alternatively, if sigma m is compressive, then the actual value I can apply is larger than that to achieve the same life. Okay? So if I now combine all of these observations, I can say the following. So first of all, if the mean stress is equal to 0, then when sigma a is equal to sigma ar, I have failure at a given number of cycles. On the other hand, if the alternating stress is going to 0, because that's what I can apply, only a tiny amount if sigma m is very large, if sigma m is increasing, sigma a goes to 0, and how large can the mean stress be? Well, the largest it can be is some critical value, which is going to be either yield, ultimate, or fracture strength of the material. Now, therefore, if you have both of them at the same time, one way to combine those effects would be by adding them. That's not the only way, that's certainly one way in which this discussion works. Let me highlight the importance of the critical stress here by writing that also in red. Okay, so now this is an equation that we have which combines the influences of alternating and mean stresses. And failure occurs at this equation, the left-hand side being 1. If you have only alternating, it can be equal to sigma AR, which comes from that equation. If it is only mean, it can be equal to sigma C, which is going to be picked among these. If you have both, there is that relation that we are predicting. Now, well, how shall I pick sigma C? Now, it turns out that there are 3 choices. All these 3 choices are possible choices, but they have different names. So first of all, if I pick sigma C to be sigma naught, I will get a relation. This relation with sigma C equals sigma naught, the yield strength, is called the Soderberg relation. Now, okay, well, let's not pick it to be sigma naught, but I'll pick it to be the ultimate strength of the material. Well, in that case, you get what is called a modified Goodman relation. So the modified Goodman relation is just an other relation that you see that has the same form. It's just that the value of sigma c changes. And finally, well, let's pick it to be something that has to do with fracture. Let's pick it to be sigma f prime, because that conveniently appears in the Basquin relation as well. And if I pick it to be sigma f prime, then you get a relation that is called the Morrow relation. So these are three quantities that act as possibilities. The template we're using is this template, and we have to remember this template because it's very meaningful. I understand what that term does, and I'm just summing them to combine those effects in a simple manner. Again, that's not the only way, but it's just one way to combine those effects. And failure occurs when the ratio is equal to 1. Okay, failure meaning failure at a given number of cycles. Now, among these relations, I should highlight in particular the Morrow relation. This is a very useful relation that we're going to use again and again. So if we don't remember anything, we should definitely remember this template with sigma critical equals sigma f prime, the same thing that appears in the Basquin equation. Okay, it's very useful, and it turns out it's particularly useful for steels. Okay, now let's move on to the graphical depiction of these three criteria.